Hey, let's get everything set up here. Make sure we're coming through all right. Usual, yep, usual check at the start of every class so I don't record videos without sound. All right, good. Okay, so as everyone is probably now aware, I hope this isn't coming as a surprise to anyone, we have an exam this Friday through next Monday. You'll see this on your syllabus. It's exam 2. The start date is the 22nd of April. That is this Friday. And the end date is the 25th. That is this Monday. So, starting on Thursday night at like midnight, or so I guess Friday morning, right? At 12 a.m. on Friday until 11:59 p.m. on Monday, exam 2 will be available to you. You same rules as exam 1. Shoot me emails if you have questions, and obviously since there's an exam, no class on Friday. Exciting. Today we're actually running slightly ahead. I probably could have done more stuff from 4.2 or 4.3 given how short 4.4 was, but all things considered, oh well, it's not going to be too important to us, and we just glossed over that little chunk. So today I thought what might be a little bit better before this exam is to kind of just refresh the story so far and where we're at. So we started out, and I'm going to pull up the old table of contents in our textbook right here. 1 second. Bada boom. Oh, there we go. Okay, so we started out with analytic functions. We began our entire class just discussing complex numbers, and my camera's contrast is nightmarishly off. There we go. Whatever. So we began this entire class discussing analytic functions. We started by talking about the properties of complex numbers, what they are, how the elementary functions are even defined in the complex plane. Then we got into a little diversion about continuity, since it turns out to be quite important if we're talking about, if we want a notion of differentiability, we definitely need a notion of continuity. After that, we got into the basic properties of analytic functions. That is, we defined what a function, what it means for a function to be analytic, which is a continuous differentiability plus the Cauchy-Riemann equations, that constraint. This gave us a nice notion of complex differentiability. We went through some of the basic notions, things like conformality, which we're going to get back into again real soon, right after this exam. Start talking about conformal mappings again, get some intuition for how analytic functions map the complex plane to itself, or subsets of the complex plane to other subsets, that sort of thing. And after that, we got into a little bit of differentiation for the elementary functions. We basically figured out, hey, we've got the elementary functions defined in the complex plane. We know what analytic functions are. We've defined that. Now, how do we differentiate these elementary functions we came up with? And so we went through and we did that. That was all of chapter 1. It was just dipping our toes in the pond of complex analysis, or the vast sea of complex analysis. After this, we got into Cauchy's theorem, probably one of the most important theorems in complex analysis. Cauchy's theorem was crazy because it just really came out of the Cauchy-Riemann equations in just like the most simple way. And it gave us a really neat way to do a couple different things. One of them was to compute contour integrals, which was the first thing we talked about in chapter 2. Another thing that it eventually let us do was use contour integrals to compute the values of analytic functions. But the way we built up to this is we said, hey, let's talk about contour integrals. Let's do Cauchy's theorem, which tells us something about integrating around closed curves and getting 0, what the conditions are for this. And we kind of looked at it a little bit more, and we were like, all right, some things seem to work, and some things we have a little bit of weird stuff going on. In particular, we really focused on this example of 1 over z. I'm gonna go back here. In chapter 2, we really focused on the example where we integrated around the unit circle, which I'll call gamma here. We integrated 1 over z, and we got out, I should put a dz, we got out 2 pi I. That was weird because everything else we kept getting out 0, right? And the issue here was that there was a point where the function 1 over z was not analytic and that inside of the unit circle, and that point was 0. So this was kind of our archetypal example for what can go wrong with not so much what can go wrong, but like what prevents Koshi's theorem from holding in a more broad situation. That is, we need not just analyticity on the path itself, but inside the region the path encloses. And this was what we used. So we looked at Koshi's theorem a little bit more, and we began to derive some additional facts from Koshi's theorem. One of them was the Koshi integral formula. The Koshi integral formula let us represent the values of functions in terms of contour integrals on curves enclosing the value of a function at a point in terms of a contour integral on a curve enclosing that point. And that was kind of an interesting fact. We built this up. We got deformation theorems and stuff like this. We said, hey, Koshi's theorem can hold for, not just circles. We can do homotopic curves that are homotopic to circles. We can do things that, go around more times, and so on and so on. And what we really got up to at the end of this was something pretty neat, which is we got the path independence theorem. The path independence theorem really drives a lot of the rest of what we do in this class, and it's maybe sort of like a fancy version of Koshi's theorem, or like the implications of Koshi's theorem. What this told us is that there are a few things that are equivalent. So we got the following theorem. So the path independence theorem, or it might have been called the path independence lemma, basically said that we have the following things are the same. And I'm going to paraphrase them so you don't have to watch me write for a super long time. So we got that the following are equivalent. 1, integral around a closed curve or I'll even just write without the dz, I'll just write of f instead of f of z dz. For closed curves gamma 2. For so here's how I'll say it. The contour integral from a path gamma 1, or of f on a path gamma 1, is the same as the contour integral of f on a path gamma 2, where gamma 1 and gamma 2 are paths from a to b. They start and end at the same place. Maybe one, go from like a to b, right? Maybe one of them goes like this, and the other one goes like that, right? We got this path independence lemma that said, hey, you get the same thing. All right, cool. Then we finally, after this, got perhaps the most interesting piece. And this piece was a big old deal. These things are all equivalent, but last one was that there exists h such that h prime of z is f of z. Now, what I really should add to all of these to make this fully specific is I should say for closed gamma in the region A, for paths gamma 1, gamma 2 in the region A, exists h such that this holds with h analytic on A, where A is some domain where f is defined. So this last piece kind of explained why we didn't get out 0 from this guy. That is 1 over z, it's antiderivative. Intuitively it should be the natural log, but which branch, right? And the issue was we didn't have a a nice antiderivative, a continuous, on neighborhoods of the origin, because the log branches in neighborhoods of the origin. That is, you got like this little strip here, where as you go around, that's supposed to be a circle. God dang, that's a terrible circle. So much harder to draw circles on your computer than it is on a blackboard. What a nightmarishly bad circle. There we go. Okay, there we go. So there was this little strip where it wasn't, you'd have a harsh jump in the value of, log, which no matter which branch you chose, along this little line, right? And you could choose things differently and maybe get around this a little bit, but ultimately it could not be entirely overcome. And so this guy didn't have this antiderivative piece, and so naturally these other things must also not hold. In fact, since we can directly compute that this holds, we ended up knowing that it didn't have an antiderivative just immediately from this piece. And I mean, the 1 and 2 path independence in closed gamut, that's not so weird because you can always cut up a closed curve. You get some squiggly path, right? You can always cut this guy apart and get, okay, let me go from here. I'm going to take this chunk here and, stop maybe there. I don't know, wherever you want. And now, hey, I've got 2 different paths from point A to point B, right? So you can always, take 2 paths like this and make it into a closed curve, or you can take a closed curve and generate 2 paths like that. So 1 and 2's equivalence is not strange, but the interesting piece is this bit, right? Or, just as well, you could use 2 instead, but that these guys are the same. The existence of antiderivatives and having 0 integral on closed curves. That was kind of the big takeaway. So we had all of this nice stuff with Koshi's theorem. We had the Koshi integral formula, which told us that if you combine it with the generalized deformation theorem in a nice way, you could say that, or even let's just say, here's what we got. We got that f of a was 1 over 2 pi I integral around curve enclosing something f of z minus a dz, right? This business, you remember that? And then we had the derivative formula where you could throw a kth derivative and just put kth powers down here in the denominator of the integrand. So we got all this good stuff out of it. It was all very nice. And then we went back to this example, so to speak. When we got into chapter 3, which went right into series representations, we started to address some things. So 1, we began by talking about convergent series of analytic functions. I'm just trying to highlight right now that this guy still hangs around in the background and has sort of been our motivation for quite a while. This has been the nagging doubt, or not even nagging doubt, but the vexing, but why? But why? What's going on here? What's happening, right? Koshi's theorem, everything was good when we, in situations that aren't quite like this one, when you get the zeros out, then you've got all the nice stuff, but we start to run into problems. So in chapter 3, we explored more fully the consequences of Koshi's theorem. Now, one of them that we were able to do using the Koshi integral formula and some other stuff is we were able to say, hey, pick a point z in the complex plane. Now, if you've got a function that is nice enough, then you can generally find some radius r such that you've got a convergent power series in this radius. Now, sometimes we found that certain things didn't have nice power series at certain points. For example, I don't see how you could write 1 over z as a power series centered at 0, right? The issue there is occasionally insurmountable, but for analytic functions, functions that are continuously differentiable and satisfy the Cauchy-Riemann equations, we could always find nice, in a neighborhood of a point where a function is analytic, we could always find a power series representation, a Taylor series. And the Taylor series, you made use of the Koshi integral formula, where we threw the kth derivative in this business right here, and we were able to get the the coefficients in the Taylor series out of that. So that was kind of what we ended up doing in section 3. What we started to get into at the very end of it, though, in 3.3, was we got back to that 1 over z example. So here, when we were dealing with just a straight up nice power series, we had convergence inside of a disk. When we moved on to Laurent series, all we really did is we attached an additional piece. So what we were doing with Taylor series is we were writing a function as something like the sum from n equals 0 to infinity of some powers, or some coefficients an z minus a to the n, right? We were writing it like this, and this was valid in here. Or in a disk. Around a. Here I'll replace z with, I should just erase that. Why did I scribble that out? It was a dumb move to scribble it out. Yeah, why not? Whatever. Okay, I'm just going to rewrite this as like a very messy looking a. If that is all right with you guys, if you can feel good about that around a. So we got power series representations in some disk. You could always find a maximal radius, right? Some things had, power series on the entire complex plane, all good. Other things, you could only go so big at a given point before you couldn't go any big, before you hit a problem, right? For example, if you took 1 over z and you expanded it around, say, like the complex number 1 plus I, right? You could only go so far before that disk would enclose 0, and that wouldn't be okay. So you could only go right up to that edge. There was a biggest radius. Okay, so there's some maximal r that a given analytic function has a convergent power series representation on a disk of that radius about that point. What we went on to now, after this, is we went to say, hey, we could attach an additional piece, and instead of doing this disk business, we could write a broader class of functions by looking at 2 pieces. One of them was exactly the same. We went from 0 to infinity, these an's, z minus a to the n, and then the other piece was maybe more interesting. We went from n is 1 to infinity, and we went, let's call it bn, z minus a to the, that's a minus a, to the negative n. Now, how these guys worked is we could grab a point, and one of them, this first part, we would have a disk in which we got convergence. Okay, so I'm going to drop the opacity down on this a little bit. So in this disk, we had convergence and everything was good for this first part. The second part was cool because instead of getting convergence in a disk, we got convergence outside of a disk. So instead we had, like a disk here, and then we got convergence everywhere outside of that. Oops, I'm making that way, way, way too dark. I want something with less opacity. We got everything outside of this. So convergence on everything outside of some disk. Naturally, what this gave us is that the region we care about, which was this annular region between the 2 disks. Now, occasionally we found things that didn't have these disks didn't play well with each other. That is, one of them's radius could be bigger, like the inside one, this pink one, could have a radius larger than the blue one. And then, there's the area of the annulus is like 0 or something. The annulus may not actually exist in that case. It could it could converge outside of something and inside of something, and the intersection of those two things could be empty. So we ran into that occasionally, but overall, these Laurent series were valid on domains that were annular regions. Okay. Sometimes the annular region about a singularity, right? If there's no singularity, then you don't end up, like, everything here is 0 and you're all good, right? If you have a singularity, something like 1 over z, then around 0 you would get this annular region. Occasionally the annulus, the inner circle, may have a radius of 0, in which case it is just a punctured disk. Or if the outside one has a radius of infinity, it would just be the punctured plane. So this was a useful little thing, but it let us get something kind of cool. So if we break all of this down, now when we start writing things out, notice if I turn this into let me even erase this right there, make it easy to see. Oh. Let me turn this into a 2. And then in between, I'll throw in this b1 over z, right? Okay. Now all these guys, this piece right here, this piece is like, a0 plus a1 z minus a plus a2 z minus a squared, and so on, right? And over here you have like b2 over z minus a squared plus b3 over z minus a cubed, and so on, right? When I take an integral around some contour enclosing some contour in this annulus, right? Let me use a different color so that it doesn't look confusing. Some contour in this annulus. When I take an integral around some contour in this annulus, notice it encloses that point. So by this antiderivative theorem, I'll actually just write it like this. If I integrate this guy around some closed curve gamma and throw a dz there, by this path independence theorem, notice all these guys have antiderivatives. They're fine, they're polynomials. All these guys also have antiderivatives. They, like 1 over z squared. That has a fine antiderivative. It's like, negative 1 over z or something, right? That's all good. 1 over z was the issue. It wasn't 1 over z squared. You got a 0 and integrate 1 over z squared dz on any curve enclosing the origin, and you get out 0 still. That guy's got an antiderivative. So by that path independence lemma, when you start doing integrals here, notice if I integrate this part dz, I'm integrating this whole thing dz. This chunk right here, when I integrate this thing about gamma and integrate this thing around gamma, these guys, I get 0. It is this piece right here that matters. That is, I'm integrating b1 over z dz on some gamma here, right? Or this should, be z minus a. Oops, z minus a. Z minus a. I'm writing it like 1 over z, assuming that a was 0, but z minus a, same business, right? When I integrate this, what am I going to get out? Once again, it's going to be 2 pi I times b1, just for the exact same reason that we got this guy was 2 pi I. Obviously, we could make gamma being a curve that, encloses some point, say like a, and turn this into z minus a, right? And you get the same thing out. This is the residue theorem. It's immediate. We actually knew the residue theorem in chapter 2. Kind of cool, right? In fact, we even did this example with 1 over z in chapter 1. So we had basically all of the ingredients necessary to understand the residue theorem quite a while ago. And that's kind of cool. really we need Koshi's theorem to make sense of all of it, or at least this path independence theorem, but residue theorem pops right out of it. So that was what we covered next. The residue theorem came after Laurent series and the classification of singularities. So when we got talking about residues, this had we had to be careful of certain things. For one, when we were classifying singularities, and what I'm doing here when I'm talking about, like, oh, we have, these representations. Notice this is only for nice enough functions. There were certain functions where we didn't have nice things, and that can happen. In particular, it was not necessarily easy to calculate certain Laurent expansions. In particular, Laurent expansions that had an infinite number of terms here were troublesome for some reasons. Calculating the B1 was not necessarily easy, but all the same, this stuff still holds. This stuff is still true, just figuring out what these values are occasionally could give us some trouble. Oops, I've made a mistake. I've closed too many things. There we go. So we talked about the residue theorem. We talked about how to calculate residues. That's where we were like, hey, we've got these formulas that got kind of increasingly messy. Some nice ones that made things relatively easier in certain situations. Some of them that were generally kind of useful. One of them in terms of determinants that we didn't really use, but were at least great for computers to use. And we occasionally ran into problems with essential singularities. That is, singularities where the Laurent series had an infinite number of BNs that were non-zero. So those guys, we didn't have an easy formula for calculating residues. But the residues theorem is still true. It's that piece that we got really simply just from that expansion we just detailed right there. After we talked about the residue theorem a little bit and how it kind of provides an analog, or maybe even a slight extension, if you want to think of it like that, of stuff like the Koshi integral formula in terms of residues now for this broader class of meromorphic functions instead of just analytic or holomorphic functions. We then took a brief diversion in 4.3 and 4.4, which will definitely not be a particularly large focus of the exam, just maybe like one problem on 4.3, maybe like kind of two, but most one problem. These guys were just some sort of bonus material to say, hey, look, all this cool machinery we built has applications outside of complex analysis. It lets us compute certain things, difficult integrals, series in nice ways. So this was kind of the story of complex analysis so far. It's relatively straightforward after we got the idea of analyticity down and the definition of elementary functions. The first thing we did is we said, okay, we know how to differentiate. What about integration? We began with perhaps the easiest type of integration we could do, which is we went for contour integrals. Okay, now contour integrals, just let us borrow all the machinery from calculus 1, calculus 2, and carry it on into the complex plane. We verified that a lot of things held, that most of our intuition remained the same, and then we got into talking about, okay, well, how do the contours matter? That is, if I go from point A to point B along a contour, does it matter how I go from point A to point B? And we found that in certain situations, the answer was no. This was the path independence theorem. Maddeningly, in other situations, we found that the answer was yes. This was the difficulty provided by things like 1 over z. That is, since 1 over z, we don't get a zero integral out along a closed curve, it means that we don't have path independence. At least for closed curves. But, some curves enclosing 0, right? So we didn't have path independence. Okay. So we went back to the ones that were nice, and we started to look and see if more of our intuition from calculus carried over, stuff like Taylor series, and it indeed did. It was great. Then we went back to the case where things went a little bit weird, when the contours maybe did matter, and we said, hey, can we extend the notion of a Taylor series very slightly? That is, can we, instead of just looking at like polynomials, basically look at rational functions? And so we looked at whatever the analog of rational functions were. That is, we made Laurent expansions, and we understood the domains on which they converged, and we used this fact, this path independence theorem, Koshi's theorem, which is just derived directly from it, to prove the residue theorem. The residue theorem then let us understand what was going on when the paths did matter. And this came about through the Laurent expansion. This coefficient on the 1 over z term became very important because that was the piece that didn't vanish when we did integrals, and that was the reason why we cared about this 1 over z example so much at the beginning of the course. So all of this kind of came together, and then we did a few kind of application sections right at the end to talk about how we could use this. And that's where we're at right now. After the exam, we will get into talking about the geometric aspects of analytic functions. We'll talk about what conformality entails. So if you recall, we were talking about how analytic functions have certain angle preserving properties. We talked about that back in section 1. We will get back to that in the next chapter, and then we will close things off with a brief discussion of analytic continuation, which is one of the coolest little tricks you can do in all of complex analysis, in my opinion. It is just one of the weirdest little things, and it really shows you just how restrictive of a condition continuous differentiability plus the Cauchy-Riemann equations, how restrictive of a condition analyticity is. And that will let us, talk about fun pop sci topics, pop math topics, like it's not that it's pop math, it's, a very important active research question, one of the most famous unsolved conjectures of all time, the Riemann Hypothesis. We'll be able to talk about Riemann's zeta function in a meaningful way. So we'll get to that after this exam. We'll do 2 more chapters, really just one part of one and then one section from another, and we'll do the final and we'll be done with the class. But this is basically where we're at right now, and hopefully it is a satisfying story. If you kind of put it all in a nutshell, it really isn't that many things. That being said, of course, there are kind of a lot of moving pieces to remember, but if you are feeling overwhelmed by stuff, just kind of take a break and look at it from the wide angle, through a wide angle lens, and remind yourself that what we're doing is we just said, hey, can we bring calculus from the real numbers into the complex numbers? We figured out what the appropriate way to do that was. Then we said, all right, we did it. Now, what things carry through? Certain things carried through very nicely, and that was awesome. Other things carried through reasonably nicely, but had interesting consequences that maybe didn't arise as similarly in real analysis. That is, complex differentiable functions were less pathological in a certain sense. There are a lot more real differentiable functions than there are complex differentiable. So all you have to think of there is that analyticity is continuous differentiability plus Cauchy-Riemann. So obviously imposing that extra restriction limits the class of functions compared to the real case. Fair enough. And this gives a lot of interesting consequences. We explored those, and this mostly took the form of looking at contour integrals and saying, hey, when do the contours matter? And we got everything out of that. So hopefully that this makes things hopefully a little bit clearer, and maybe situates your mental state a little bit better before the exam. If not, sorry for taking up the time there, but this is the story so far. So if you have any questions going into the exam, please let me know. Shoot me emails. If you have questions while you're taking the exam, please let me know. Shoot me emails. And if you're feeling concerned about the class, please let me know. We are getting to the end of it, and if you don't talk to me soon, it will be too late for us to do much of anything if your grade isn't where we want it. So, yeah, awesome. I think we'll call it for tonight, and yeah, I'll see you next week. Good luck on the exam.